In the first video in this chapter, we defined the average velocity as a change in position or displacement divided by the time taken. We used the example of Usain Bolt running a distance of 100 meters in a time of 9.58 seconds to determine his average velocity over that distance to be 10.4 meters per second. But Usain wasn't running at this velocity for the entire time. At the beginning of the race, he was stationary. He then accelerates from rest to some maximum speed, then tries to maintain that speed for the rest of the race. He then slows down after passing the finish line. So his velocity during the race has varied. In the early part of the race, his velocity was slower than average, and in the later part of the race, his velocity was faster than average. In the last video, we looked at how the velocity can be determined on a displacement time graph, with the velocity being the gradient of the line that connects the start point to the end point. This gradient represents the average rate of displacement per unit time over the duration of the run. But as Usain started much slower at the beginning than at the end, his rate of displacement would look something more like the red line in this graph. We can see that the gradient of the graph is less at the beginning of the race and higher afterwards. The gradient at any point in time along this line gives us the instantaneous velocity. So we can see that over a large duration of time, the gradient of the line does not give us an accurate profile of Usain's velocity at any point in time. To determine the more accurate profile, we can reduce the time interval to a smaller value. Let's say half of the time. We find that now we have two lines with two gradients. The gradient of the first line represents the average velocity in the first 4.79 seconds, or the first half of the run, while the gradient of the second line represents the average velocity in the second half of the run. Now let's reduce the time interval even more and consider the first 2 seconds of the run. Now the gradient of the line represents the average velocity during the first 2 seconds. Let's reduce the time interval even more and consider an interval of 1 second, say between 1 second and 2 seconds. Now the gradient of the line represents the average velocity during the time interval of 1 and 2 seconds. We can reduce the time interval even more. Each time we do this, we notice that the gradient of the line becomes more accurately matched with the gradient of the displacement time curve. If we keep reducing the time duration to smaller and smaller intervals, we will eventually reach the limit of instant time, and the gradient at this point then represents the instantaneous velocity. Therefore, instantaneous velocity is defined as the average velocity in the limit that the time interval approaches zero. This is more commonly known as a derivative of the displacement time curve, or the rate of change of position with respect to time. So comparing average and instantaneous velocity side by side, we can see that average velocity deals with a longer time interval between 2 points of position, whereas instantaneous velocity can be determined at any point along the path. Now let's have a look at an example. Consider the motion of an object in the following graph, with its position being described by the formula x is equal to 2.1 times t squared plus 2.8 meters. What is the average velocity of the motion between 1 and 3 seconds? From the definition of average velocity, we can see that the time interval is between 1 and 3 seconds, so the duration is 2 seconds. We now need to work out what the displacement is during this time interval. The formula that describes the motion is given by 2.1 t squared plus 2.8 meters. The position at 1 second can be calculated by substituting 1 second for the time into the formula. This gives us a position of 4.9 meters. That is, after 1 second, the object is 4.9 meters from the starting position. The position at 3 seconds can be calculated in the same way by substituting 3 seconds for the time into the formula. This gives us a position of 21.7 meters. That is, after 3 seconds, the object is at 21.7 meters from the starting position. Now that we have the positions, we can substitute them into the average velocity formula. So the displacement between 21.7 meters and 4.9 meters is 16.8 meters, and the duration between 3 seconds and 1 second is 2 seconds. Thus, the average velocity is given by 16.8 meters divided by 2 seconds, or 8.4 meters per second. On the graph of the displacement time curve, we can plot the positions at 1 second and at 3 seconds. The line that joins these two positions will have a gradient equal to 8.4, which represents the average velocity of the motion during this interval. Now let's determine the instantaneous velocities at 1 second and 3 seconds. For the instantaneous velocity, we first determine the derivative of the displacement equation. The derivative of 2.1 t squared plus 2.8 is 4.2 t meters per second. Now we can substitute the times into the velocity equation to give us a velocity of 4.2 meters per second at 1 second and a velocity of 12.6 meters per second at 3 seconds. To verify that our answers are consistent, let's consider the average between our two instantaneous velocities. The average of two numbers is the sum of the numbers divided by 2. In this case, our two numbers are the instantaneous velocities at 1 second and 3 seconds. So the average gives us 8.4 meters per second, which is the same as previously calculated. Now it's time for you to have a go at calculating the average velocity between the time interval of 2 and 5 seconds. What is the instantaneous velocity at 2 seconds? What is the instantaneous velocity at 5 seconds? In summary, the instantaneous velocity is the average velocity in the limit that the time interval reduces to 0. It is the rate of change of the displacement with respect to time.